Tactile stimuli. In 1962, another series of experiments was carried out in the analysis of the cues involved in the aggregation formation of Clibinarius tricolor. A large enamel pan was visually divided into 4 quadrants by placing small spots on the sides of the pan. The bottom was covered with sand, and 2 sets of items were placed in 2 of the quadrants. A set of shells from which the individuals of Clibinarius tricolor had been removed was placed in 1 quadrant, and a set of small stones of approximately the same size and coloration as the shells placed in another. In the first series of tests, the shells were washed only with seawater. In the second series, the shells were first washed in 70% ethanol and subsequently washed in seawater. The test individuals were placed in the center of the pan and their position noted 5, 10, 15, and 20 minutes later. The quadrants of the stones and shells were altered after every 5 tests. The results are listed in the table below, along with the chi-square values and probabilities for the distribution of positions among the 4 quadrants, chi-squared 1, and of the distribution of positions between the stones and shells, chi-squared 2. A table I am not reading. The results of these tests indicate that the crabs do orient to the shell chemically, or perhaps by chemotactile means, and to shells or stones tactilely or visually. Apparently, the substance oriented to can be washed off by ethanol. As described in earlier sections, the individuals of the genera Pagurus and Pilopagurus show a distinct shaking behavior pattern when another individual crawls upon their backs. This behavior pattern tends to dislodge a crab that is on the back of the shaking individual. Since specimens often went through this dislodging behavior pattern when the individual to be dislodged appeared to be out of their visual range, it seemed that this behavior might be initiated by tactile stimuli. The possible existence of special chemical or sound cues was not tested. Pilot experiments indicated that individuals would respond to artificial wire legs placed onto their backs. A series of artificial legs was fashioned from steel wire, 1 millimeter in diameter and about 9 centimeters long. To vary the weight of these legs, lumps of clay of varying size were attached to the wire. The legs were weighed on a Ryers and Zune type PM balance. The legs were supported in such a way that when balanced, they made an angle of 30 degrees with the balance pans. A series of 50 individuals of each species was tested. The specimen to be tested was placed in a culture dish, 8 centimeters in diameter, with sand on the bottom. The water level in each dish was such that the highest portion of the test crab's shell was just below the water surface. The animal was undisturbed for 5 minutes. It was then tested with all the weights used for the species. See Table 10. Each test leg was placed on the highest area of the shell of that individual. Approach and placement were from the back of the crab to minimize visual disturbance. The legs were supported in such a way that they made a 30-degree angle with the crab's substratum. There was an interval of at least 1 minute between the testing of different weights. The weights whose placement caused dislodging shaking were recorded. Following testing, the specimen was weighed in its shell and then extracted and the length of the cephalothorax measured. Subsequently, the average weight responded to by each individual, who responded to any weight, was plotted against its cephalothorax length. A Pearson's R correlation coefficient was determined for the distribution, and the probability of such a distribution occurring by chance alone determined from statistical tables. The response distributions and the statistics for each are given in figures 38, 39, 40, and 41. Observations during the testing and initial inspection of the results suggested that the size of the shell an individual was inhabiting affected its responses to the weights. That is, individuals of the same size varied in their behavior according to the weight of the shell they were in. A weight length index value was obtained for each specimen by dividing the combined animal shell weight for each specimen in milligrams by the length of the cephalothorax in millimeters. This index failed to correlate more closely than the cephalothorax values with the average value of the weights thrown off. However, it did show some correlation in two species with the number of different weights to which individuals responded. See table below. The negative correlation in Pagurus bonarensis and Pylopagurus operculatus indicates the tendency of individuals in relatively lighter shells to react to a greater range of stimuli. Figure 38 and 39. Relationship of size and average weight eliciting dislodging shaking in Pagurus miamensis and Pagurus bonarensis. Table 10. Weights used in analysis of dislodging shaking stimuli. Figures 40 to 41. Relationship of size and average weight eliciting dislodging shaking in Pagurus marshi and Pylopagurus operculatus. Correlation of weight length index with number of weights thrown off. Pagurus miamensis R minus 0.073, P greater than 0.1. Pagurus marshi R 0.039, P greater than 0.1. Pagurus bonarensis R negative 0.240, P 0.1 greater than 0.05. Pylopagurus operculatus R minus 0.255, P 0.1 greater than 0.05.